Physical and Chemical Institute of Ukraine, and today I would like to talk about fatigue growth in operated gas pipeline cells. This research is supported by NATO in the program Science for Peace and Security, and some results of this project you can see in the talk of my colleague in the beginning of this section. So I will not repeat the background and motivation about current state of Ukrainian gas transmission system. However, I should say some words about the reasons of this part of work. Because usually gas pipelines are considered as a long-term operated object subjected during their long-term service to combined action of corrosion environment and working stresses. And these working stresses are typically static tensile stresses from the pressure of transported hydrocarbons. However, fluctuating stresses are also possible in the course of operation. It could be caused, for example, cyclic temperature changes or other factors, and they are also should be taken into account in the assessment of pipeline serviceability. So in this work we try to find out regularities of particular growth of pipeline steels after their long-term operation. And here you can see our materials. These are pipeline steels of different strength grade, and service time of these pipelines varies from 25 to 37 years, and the experiments were performed in air and also in NS4 solution, standard solution simulating the soil environment. And besides fatigue testing, we also did some observation to evaluate some regularities of particular growth in our tested steels. This slide illustrates the changes in fatigue behavior of our steels after long-term operation. And we can see that novo-sectional differences was observed in the second part of fatigue growth curve for steel in the initial state and after operation. However, some changes could be detected in the near threshold region, namely threshold values of stress intensity factor for the steel after operation is somewhat lower than that in the initial state, and this is a general tendency for all tested steel, as you can see from this picture. Looking at the SAM images, you can see that fracture surface after the test of steel in initial state has more or less smooth relief, whereas after operation the relief is much higher. And we suggested that this is the result of multiple crack origins, which in turn caused by damaging development and accumulation in the steels during their long-term operation. And these bright areas are the traces of the contact of crack edges during the loading cycle, indicating roughness-induced crack closure. If this crack closure effect was taken into account, we suggested that these differences in fatigue behavior of steel would be more noticeable. However, these precise experiments require a lot of time, so it will be the subject of our further investigations. So let's continue with the effect of corrosion environment on our steels. Here you can see the fatigue crack growth curve for the steel 17H1S in air and in the solution. we can see that threshold values of stress intensity factor is somewhat higher for the steels in environment comparing to the test in air. And the reason of that is crack blunting due to effect of environment. And considering the second part of the crack growth curve, we can see some acceleration of the peak crack growth. It's almost negligible for the steel in the initial state. However, it's quite essential in the steel after operation. And looking at the fracture surfaces after these tests in solution, we can find the elements of intergranular fracture in both pictures and also secondary cracking. However, in the steel after operation, these cartographic features are much more noticeable. So similar results were obtained for the steel X70. Also, we can see the acceleration of fatigue regrowth on the middle part of the fatigue regrowth curve. And as we compared fracture surfaces obtained after the test in air and in solution, we will find the similar fracture peculiarities, cracking, secondary cracking, intergranular fracture, and also in general relief of the fracture surfaces is higher. So the next part of this work is devoted to some aspects of experimental modeling, and here I would like to present our methodological approach to fatigue testing, which allows us simulation of working condition of pipelines. Because we have shown by our previous experiments that hydrogen can form at the internal surface of the pipe as a result of corrosion processes in the external surface of this pipe. And it's well known that cracks typically occur at the external surface of the pipe, initiating from the pits in the places of damaged isolation cover. And the question is in possible influence of hydrogen formed here to the crack growth on the opposite side of the pipe. And here you can see a setup of our experiment, and the main peculiarity is that our specimens is only partially immersed in the electrolyte in such a way that our cracks is always above the level of environment. So under a condition of hydrogen charging, the only way for hydrogen to reach the crack tip is diffusion through the metal. And the results of this simulation are present here. So the basic curve is air, and this acceleration of crack growth is due to hydrogen. Hydrogen causes little crack growth, forming a plateau where the crack growth is independent on the applied value of delta K, and such situation is typical for environmentally assisted cracking. And when you have several factors influencing the mechanical behavior of material, in our case this is hydrogen and mechanical factor, one of them always prevails, and in the presented test conditions we can see that hydrogen plays a key role in this fracture propagation. And it was confirmed by fractography. You can see the fracture surfaces after this experiment. can see intergranular fracture and a lot of cracking. So hydrogen in this case leads to embrittlement of grain boundaries. And this effect is really essential. And one more methodical approach aspects is validation of procedural accelerated in laboratory and degradation. This method, this procedure has been recently developed in our department by Professor Niki Fortune and co-workers. And this method is based on a well-known method, well-known standard method of artificial aging. However, it was modified by preliminary hydrogen charging and also applying tensile stresses to specimens. And here you can see comparison of the Pettit-Craig-Grove curves for the steel X70 after 37 years of operation and after our accelerated degradation. And we can see that results are similar, are comparable, and also fracture surfaces for this steel confirm this statement. Changes of material after operation and after accelerated degradation is similar. So this is we suggest that this is evidence of that our method is applicable for simulation of operational degradation of pipeline steels, and in this way prediction of the properties of pipeline steel after their long-term operation. So in conclusions, I think I have done to read it. So long-term operation leads to a decrease in the threshold values of stress intensity factor of pipe steels, particularly it is higher for operated steel due to multiple crack origins. So solution under fatigue testing promotes occurrence of intergranular fracture elements with secondary microcracking, more noticeable in operated steels. Hydrogen formed in the inner pipe surface can penetrate pipe wall and affect the crack growth at the outer pipe surface, and fracture behavior of the steel after operation and in laboratory degradation are very similar, proving the validity of the elaborated method. Thank you for your attention.